Imagine, before we get into this, imagine you had a trace with two primaries. Yes? One, just straight up and down. And this is the reflection coefficient from the top one, the time it arrived. The amplitude is second because it has transmission on it. And the time it arrived, yes? You can solve from this data and produce alpha 1. There's a relationship alpha 1, yes? And the data, the linear. Okay? So, I guess you can't see this. Probably not. See? Everyone can see here? All right. Alpha 1 here of Z looks like 4R1 H of Z minus A every side plus 4R2 prime H of Z minus B prime, where A and B are the actual depth and A and B prime are where water speed will locate. Yes. So let's say C0 and C1, and this is bigger, so it will be too shallow. Yes. Too shallow. So what, if you take this form and put it in that, we're going to assume now a one-parameter world where only velocity changes. Yes. If you look at the analog of there was some kind of alpha 1 derivative in integral, alpha 1 minus beta 1. Yes, there were some things running around outside. If there's in the world in which there is no density change, that the formula, the first nonlinear term in the inverse series has a term like this: alpha 1 derivative of z times the integral 0 to z alpha 1 of z prime dz prime. Just you take my word for it. If now what I'm saying is alpha 1 of z is just the integral of these. Okay? Gives you a step function at the right depth and another step function at the wrong depth because it's water speed. Yes? If you only took this, only have a data with one reflector, and it is at water speed, yes? And you take that alpha 1, if you only have one primary, and put it in this formula, you get 0. You understand? This is a moving, this is an indicator, do you have an imaging problem? Yes? If you put these two terms in, both outside and inside, it will indicate that at Z is B prime, you have a problem. And it says, and it multiplies, what it gives you is B prime minus A. You get some kind of indication delta of Z prime minus B, or Z minus B, times, Z prime minus B prime, and B prime minus A. So what this is the depth that it predicted with water speed. This is the shallower, right? This gives it in its terms. In other words, this is like time, T2 minus T1 with C0, you know? Because it doesn't have the right speed. But it gets an estimate of how big the issue is and where the issue is. Okay? That at B prime it has an imaging field. Yes? Just giving you some, this is all analytically doable. You know I just said because of those kind of functions. It just gives you some sense. So that's the case where there's only velocity. When you have velocity and density, it has to make a decision. Is that reflector, yes, is one of these reflectors, perhaps the shallow reflector, only a density variation? And it doesn't have anybody to talk to. There's no velocity change. So you can image both with C0. Understand? Okay. Anyone wants details of this, we can send you papers. But it's interesting in terms of what that does, one parameter, two parameters, three parameters, even more so. Okay, there's several motivations for this work with Jinlong Yang and myself. One is, we have a lot of activity in FWI, which was doing P wave, and now increasingly are at times using multi-component. Yes, you hear about that, elastic FWI now. So a question is, we just gave a talk a few minutes ago saying, if you're looking for changes in elastic properties, that the direct inverse for that says you need multi-component data, PP, PS, and so on, if you want to do anything nonlinear on it, and it tells you what to do with it, yes? It tells you the formulas to multiply that data to get linear and quadratic and cubic estimates, yes? Not updating linear, you get a linear and a quadratic and so on. So a reasonable question for us to ask is, let's say people are saying, we understand you need multi-component, you know? We hear that more and more, and we say you need multi-component. If you agree on the data, are your algorithms going to be different? Yes? Yes? What's the difference? So what this exercise is, I said, let's design an experiment where the data is as simple as can be, yes? It's just, there's no issue of multi-component. So in other words, we want to isolate just a plane wave went down, it hit a single reflector, came back. What does the inverse scattering series do to get C1 from that reflection? What exactly does it do? Then what does iterative linear do? Assume you have no bandwidth problems. Okay? We're not looking at that issue. And because, in fact, that has issues, as we said, if you're doing a variable background. We're going to arrange it so that doesn't exist for the iterative. They have perfect updating, understand? Analytic updating of the background, understand? Just so we, in a pristine sense, examine only algorithm, not data issues with algorithm. So that's what this is about, yes? I thought it could be useful because we'll see, are they equal, right? Are they equivalent? Okay, so this is, we don't need an introduction. We've seen this, okay? What we're going to do is, in our usual isolated task business, we're going to say, imagine that free surface multiples have gone, internal multiples are gone, you're at the right location, yes? And you don't know what changed. Okay, so in other words, all those other tasks are being ignored, yes? We're isolating to parameter estimation. Clear? Okay. But we're using that machine for that. And then there's another approach, which we'll call linear iterative, which says, let's say this is the actual Earth model, this is some reference, this is the data for the actual Earth, this is the data for your reference, and your idea is to try to, if you choose M0, can we find M minus M0 so then we'll know M? Yes? Choose M0, yes? And so a typical way that is carried out is to write a Taylor series like this, yes? A Taylor series where this is your actual data, reference data, and you have a Frechet derivative of sensitivity matrix times M minus M0, and of course it goes on, but this is being truncated, and it's going to be, if you have your actual data, if you have your reference data, and you can determine this, you can invert this and get estimates of that difference. So that's an approximate linear, that is a linear relationship. That relationship is approximate, yes, because you truncate it. So there are times when that derivative is calculated with two models, yes? as a finite difference. In other words, you move to some nearby model in some direction, and you calculate the data at the nearby model minus the data at the model, divide by some kind of delta M, yes? And that will then be put inside for that f prime derivative. Yes. We don't want to do that because that's an issue. Yes. We don't want to let the iterative linear suffer that issue. Okay. We're going to give it the exact Frechet derivative. So we start the same. Okay. You understand? I don't want that issue there. That is an issue. Okay. And there are other issues, you know, updating band limit, all this. All the inverse steps in the iterative are going to be arranged to be analytic. That's not normal for data, yes? So they both will have analytic capability. The reason is we're not trying to cast dispersions here. We're trying to figure out what is, under perfect conditions, the difference, yes? So then what you would do, if you got that, some estimate of m minus m0, let's call it delta m, capital M1. You use that equation on the last page. You got a delta M1. What you would do with delta M1 is this m minus m0 is, you could take delta M1 and add it to M0, yes, and get an estimate of M. Yes? That's a first estimate of M. Take the difference, yes, and call it an estimate. Another thing you can do, which is what is done, is take delta M1 and not use it directly to estimate the C1, you know, but use it to change the reference. In other words, the idea is try to make the reference closer to make C0 closer to C1 so that linear approximation is more accurate. That's the idea. Okay? In other words, take this guy and change the reference. Yes. So, before everybody follows what I just said, in other words, we're going to take an estimate of the velocity below, which we know is not the velocity below because it's a linear, yes? And just say I'm going to start over and make that a new C0, yes? C0 changed by that delta M. And that will be closer because it's an estimate of C1. That new reference should be closer to C1 than C0 was. And hence linear should get better and better. That's, I'm probably not saying it right, but that's the idea. Clear? Yes. By the way, that changes the physics of the problem. That step, what we just said, because in our world, we have something below us. In other words, we assume we know where the experiment is. But that down below somewhere, we don't know. And it's that down there that we need to find out. In this procedure, you're changing the actual physics. You're saying where you are is being changed. Okay? In other words, C0 is where we are. We're trying to find that. You understand? The C1. But so if I had to argue, as I did in the group when we were doing this, the commitment is to find out what happened below the boundary. Don't worry about what you're changing up here. Yes? Just do it. Okay? I'm okay with that. That's the procedure. But it's different in the other, in the inverse scattering. This will stay C0. Yes? And you just try to keep finding a linear, quadratic, cubic of that jump with one unchanged reference. That's why those G zeros never change all the way down. Okay, you don't go back and update. Now, does anyone have any questions? So what we want to do is give the linear iterative the benefit of how to do this analytically. Yes? Well, you get that from the inverse scattering. Yes? In other words, we don't want to do a finite difference thing. We'll give them how you get that exactly and just hand it to them. And every time they want to update, we'll still give them that. Yes? Okay, so let me explain what I'm talking about. If you look at this, there's some kind of truncated forward in the language of scattering theory, right? Blah, blah, blah. We just truncate, yes? Like they do in the, yes? And we said, use this forward. In other words, let's talk in scattering theory language like we were iterative linear, yes? Clear? So what we would take this forward, this nonlinear thing, yes, and cut it. And then we would, this would be your data of the actual, this is the data of your reference, and this thing, this G0, G0, is the F prime of M0. The V is the delta M. You understand? V is the difference in the two models. V is the difference between the operators of these two. Yes? That's delta M. Do you get the translation? Yes. So the benefit of looking at this is you get an exact Frechet derivative or sensitivity matrix with one model. You don't need a nearby model. Yes? You get one model, and you can do this for velocity only, or density and shear modulus. In other words, you get a slightly different form, a gradient on G0 or something, but it's analytic. At that, you get the Frechet derivative directly on the model you're interested in without a nearby one. Understood? From that form. So, clear? So let's go and find what that is. In other words, in the language of the scattering business, it's data G0, V1, G0. See, here you have to say you truncate it, because this is a forward series. And you say you cut it, and you're going to use a forward series as some inverse machine. Inverse scattering, excuse me, doesn't do that. It doesn't use a forward series, a forward problem in an inverse sense. It has equations like this. Inverse equation. This is the inverse equation. This is the equation for V1. That's a direct, understood, V2 and so on. In other words, it doesn't treat the inverse as some modeling run backwards. There's a modeling, and then there's an inverse series. Yes? Okay. That inverse geometric. But this first term of the inverse looks very much like this. If we call G minus G0 data, yes? In other words, and so let's, for the problem we just mentioned, go and find that exact Frechet derivative. This is doing a lot of talking. Too much talking. Okay, so here's the problem. It's saying that G0, G0, to undo it is generally, for a homogeneous background, is a Stolt migration. We mentioned that before. In general, but in this simple problem, it's much simpler. What that whole thing boils down to, we're going to treat this kind of acoustic business. You're used to this, yes? Alpha. Okay. In other words, we're setting this up to get that Frechet derivative. In other words, that linear term, we have to look at what does V1 look like, what are G0s, and then go find V1 and give that G0, G0 to the iterative linear people. to do their Crochet derivative. You understand? So Simon Shaw, in the problem of a one-dimensional acoustic medium, if you give a trace, d of t, yes, you do an integration of the trace and get alpha 1 and z. That's analytic form for solving G0, k squared alpha 1 G0 is your data. You would analytically invert it. Yes? Clear? That's for a variable 1D medium. If you have a single reflector, this guy is just some, like over there, R1 delta, and it produces a heavy side. Yes? A spike integrated. So it gives you a step. It says the linear estimate of that jump between C0 and C1 has this amplitude, and it jumps at the right place. Yes? Because it has the right velocity. Yes? Understood? It's a step. This is not alpha. This is the linear estimate to alpha. Yes? So, this then gives you how to find f prime of f0. In other words, if we consider this delta m there like delta m1, yes, because it's a linear estimate. In other words, this here produces an analytic inverse to this or this. They're the same, yes? It's just a different way of talking. Did you follow? This is the same as that. For the case of a single reflector, that's the alpha 1. Yes? So we're going to give the iterative, that alpha 1, and give the inverse series, that alpha 1. Giving it the benefit of, and not only that, we're going to let the iterative, in other words, every time it changes the reference, it's still a new reference and it's still C1. So it's going to get a new reflection coefficient and just multiply the new one by 4, yes? And you'll get the new alpha 1. They keep looking for new linear, yes? Understood? So we're giving them not only a linear start, but how to linearly update, yes? In other words, there's a whole bunch of practical issues in the iterative linear we alluded to before. You got a new inverse, you got the data is in it, right? All that story, yes? Remember before, the V1 cares about the data, and now you got a new L0, that's generalized inverse. We're avoiding all that, yes? We're saying, those things are real, but I'm saying, give them the same, give the iterative the benefit of what the inverse scattering understands how you express the linear term analytically. Clear? And just compare. Does anyone have a question about that? We're trying to be compared just the algorithm, yes? Okay. We're not saying, well, you guys couldn't find alpha 1. You'd be searching around in your epsilon world, you know? Forget about that. Let's say they had the right one. You gave it to them. Now what does the machine do? Yes? So, the inverse series, Simon Shaw, Shuley, that's Shuley. Okay. Sometimes no, it's Li Shu. I think in Chinese people call it Li Shu. That's okay. It's the same person. He commutes. So these individuals computed, in other words, you can get alpha, the higher order terms, alpha 1, alpha 2, alpha 3. For a 1D medium, you have an analytic expression, yes? This is alpha in terms of its linear, quadratic, cubic, and so on. That's for any V of Z medium. For just a single reflector, you get this alpha 1 just becomes 4 R, H, and just forgetting about this H, that H is going to run everywhere. Just look at the amplitude. In other words, 4R minus 8R. You understand? We're just putting in there essentially 4R because it's overall has an H of Z minus A in it. Yes? They're all getting the right location. They're just updating the amplitude. This guy here sums to that form, as you can see, yes? And it always converges. The ratio test, will show you that no matter what the R is, that series will always give you alpha. Yes? Instead, it doesn't matter how big the R is. Okay, there. I saw skepticism. That's the ratio test. You understand? That's you take n minus 1 term over n, yes? But the next n goes to infinity, and it comes out with n goes to infinity, it's the absolute value of r, which is less than 1. Yes? And hence, it's always convergent. Yes? So that simple case, the seeking that perturbation in the simplest perturbation in the world always converges. So let's look at, that's the inverse series, yes? Linear, quadratic, cubic. The other is not going to do, the other is nonlinear, but it doesn't talk, it's nonlinear in terms of the original data. Iterative is nonlinear in terms of the original R, but it's always doing linear steps in terms of the new R, because it gets a new reference. Understood? So now we're looking at iterative linear. So use the first estimate of alpha 1 to compute a first estimate of the velocity. Call it C11, yes? With a formula like this. Where, because the definition of the alpha like that. So you get a C1 equals C0 times 1 minus alpha. Like that. So this is the definition of alpha. Yes. So what this is saying is, go find your first estimate of alpha. Why are we calling it alpha 1, 1? Because it's always going to be linear there. In other words, there it's going to be iterative, linear. You understand? You're going to change the reference to linear again. Change the reference to linear again. That's why they call it iterative linear. Yes? Okay. So, what we're saying is, the first estimate of C1 comes from that alpha 1. Yes? You put in alpha 1, you get an estimate of this C11. There's not going to be an alpha 2. There's going to be a new alpha 1. Okay? Because we're going to take this estimate of C11, of C1, called C11, and call that the new C0. Yes? Yes. So the new C0, whatever we call it here. So that first estimate of the velocity below is made the new reference. That's what just happened there. Yes? We made this equal to that. Yes? Okay. So, and then you keep doing that. In other words, now you have a new reference, and here's that original. In other words, we're going to keep doing linear. That's why you don't call it alpha 1, alpha 2. It's alpha 1, 1. It's the first linear estimate, yes? Now we're going to change the reference and do alpha 1, 2. Means the second estimate of alpha 1. The alpha there is changing. See, it's a totally different mindset. Inverse scattering, there's one alpha and one reference. The reference is C0, and the alpha is what it takes you to get from C0 to C1, period. And you're trying to find that term by term. In the iterative linear, you have a first linear estimate, 4R, yes? You change the reference to be equal to the estimate of C1. So making the C0 closer to C1, yes? Then you do linear again. So you're going to have a new alpha 1, yes? You understand why there's a new alpha 1, not an alpha 2. So that's why you're seeing this notation. This doesn't mean alpha 1 squared. It means alpha 1 the second time you iterate, yes? This gives you the number of times you went through that. And we're giving it the benefit of what you know from the inverse scattering, the analytic. It says whatever that R is 4 times that R, yes? Understand? So at every step, it's having that.
Yeah, I think we're well used to doing iterative linear. I think everybody in this room has done one of iterative linear.
Okay. Good. Well, maybe it's an education for me. Okay. Because I didn't realize that iterative linear actually changes the physics of the problem. If you change what you PU in the unknown, which I'm okay. Again, I'm an academic and far from pure. But the inverse scattering, where you are is assumed to be known and remains assumed to be known, and the only thing you don't know is what you started out not knowing. Yes, and you try to find it. Okay, but so if that's true, I'm happy. So then you know this will run into a problem. So the problem is simply stated. That step, the step is the step that can run into a, first of all, there are times when that will converge. This will converge. So let me try to summarize everything. There are times when the inverse scattering business alpha 1, alpha 2 will converge. In fact, it will always converge. We just showed that with the ratio test, yes? There are times when this will converge, yes? Where you'll get to C1. Yes, and there are times it won't. It won't, and when it won't, it's very interesting why it doesn't. Okay, so when they both converge, the inverse scattering series converges faster. You'll see, gets to that result faster. Is clear? The main message here is they're not equal. Okay, when you see the calculations, with one term, second term, you understand the graphs, they're not equal. So in the multi-parameter world, or multi-component world, if we say do this with these matrices, and someone says it's the same as iterative linear, this is answering in the simplest problem in the world, they're not equal. Yes? So they're definitely not going to be equal there. You understand? I had several motives for looking at this. So the issue here is this is tied. The issue here is this is tied to model matching. It's trying to make the data actual and reference smaller data. Okay, what am I talking about? When as soon as it gets the first iterate, it makes a new reference. It makes a new reference. That can break down. In other words, if you have a formula, this is like alpha 1. If you get a formula with alpha 1 where this is bigger than 1, this is imaginary. Understand? You can't, in other words, this is depending on change that medium above it, yes? There are times when you'll see the answer is does not compute. The other doesn't do that, so it just goes, finds its alpha. And when it's finished finding it, it says, here, use that to go find the velocity. It doesn't, at every step, say, go find the estimate of the velocity, estimate of, okay. So there are several levels of communication here. This happened very recently. We just, Jinlong and I just did this recently. This is a situation where the iterative will not compute. If you have a reflection coefficient bigger than a quarter, you can't get the new velocity. You can't. You get an imaginary number for the velocity. Yes? The inverse scattering just gives you alpha 1, alpha 2. Just keep doing that. So here's inverse scattering, where you're plotting alpha actual. Alpha actual is a number. It's the jump. Yes, it's the jump. And here it's doing this, and within a few steps, it gets it for this size. And the iterative alpha 1, what this means is there's an update in alpha 1, and that alpha 1 goes to 0. Yes? As it should. In other words, the linear estimate should get smaller and smaller as you make the reference closer to C1. Yes? So it's doing what it should do. But the meaning of this is totally different than before. This is, the linear estimate is changing. Yes? Okay. This is velocity estimation for under a case where in convergence, C actual is this, and the C, this is the iterative, and this is ISS. For when it works, small reflection coefficient, they both work, they don't work at the same rate, as you can see. And this is for a big reflection coefficient. A reflection coefficient of 0.25 is huge in the real world. Yes. So it's not. There are several different questions here. The one question is, are they the same? They're not. Okay. So that's for me an important point. And then relative benefits of things is separate. If you're in this, where you take a reflection coefficient bigger than 0.25, you can't compute. What does that mean? When you get alpha 1 here, 1 minus alpha 1 is negative. And you get the square root of a negative. You can't get a new reference. It's tied to getting a new reference, you understand? The inverse scattering doesn't say, I'm going to change the reference. You just go find yourself an alpha. So they're different, and I thought you'd find that perhaps interesting.
Although in real life, you'd be calculating these derivatives and stuff numerically as you go, oh, too big a step, scale back, scale back.
Well,
Yeah, if you have box constraints or
Well,
something to your optimization.
there are, I think the situation is a lot worse for the iterative if you talk about the real world. Because in the inverse scattering series, you have that analytic inverse in the real world. You got G0. You know, you do Fourier migration, yes? And you get alpha 1, you do Fourier migration, you get alpha 2. The G0s are the same. In the iterative linear, in the real world, since you brought that up, you get the first estimate, alpha 1, it has data in it. And you're going to take a data, right, to form a new, remember the story? Or in iterative linear in general, both linear, iterative, and inverse scattering start with this. Whether or not iterative linear understands that or not is a different story, yes? they will call it f prime of m0 times delta m some 1 equals data. Yes, go invert this. So what's the point of getting this? In this language, the point of getting this is you're going to change your reference. We gave it an analytic way to get this, yes? And every other step, because we don't want to tangle up issues of noisy, band-limited data, and we're updating. You follow? In the real world, if you're dealing with this and you want a new inverse, you're going to take your L0, or whatever your M0 is, you'll solve for this by inverting this, yes? And this is part of delta M, yes? And your delta M, you're going to add to L0 in some way. We'll call it V1 or minus V1, and this is your new reference, yes? This, if this was analytic, this will not be, because V1 will care about data. In other words, V1 equals, let's say, G0 minus data G0 minus. This is data. V1 is band limited, noisy, like your data. That's not a problem if I want to multiply V1 by itself. Yes? But if I want to invert a new operator with this, this is not going to be analytic anymore. This is going to be numeric, because this is numbers, yes? I'm saying that's a major difference. If you have a single unchanged inverse, which is analytic, compared to an inverse which is constantly changing by a new data, yes? But, so for me, that's a huge difference. But I said, forget about that difference, yes? You understand? Arrange the problem that doesn't exist. So that the achievement of the new inverse is that R is perfect, yes? And that alpha 1 is perfect for R. Just look at the machine of iterative versus the other, okay? If you find that interesting, that's fine. The result is that there are conditions under which they both converge, yes, and will be useful. When they both converge, the iterative, it converges slower, and there are times when the iterative doesn't converge, it's not computable, because it's committed to finding a new reference, and that can't. The other doesn't do that, so it never sees that issue. You understand? It just keeps finding alpha, which is, okay? I thought you might find it interesting, okay? I found it interesting. And so, what does this have to do with us? We have this wonderful apparatus for parameter updating from Ian, from Hung, from Shuli, from people, right? Parameter estimation, elastic. Understood? So, when should we use it? Yes. So you get a nonlinear estimate. Well, Ian worked with Doug and Bob Keys, and they found that was interesting and important in 4D. Yes, they gave them a way to distinguish between two things that linearly were too close. A pressure change and a velocity change were too close linearly to know which it was. Once they got a nonlinear, it's separated. So we want to know when these different tools, either for 4D or otherwise, yes? Saudi Aramco is interested in 4D kinds of issues. When are these amplitude issues that we have, yes, relevant? So we're going to work with Doug, and we're happy to work with all of you. We're just pointing out it's not iterative, okay? Whatever else you want to, we're happy to have these, for you to have these slides. Last but certainly not least, the next talk is by Jim Mayer, who's going to give an overview of code delivery, yes? What is this program delivered? what are we gonna be delivering, yes? What codes, what are their properties, yes? And then I'll say some final words. That'll be the day. I thought this would be an interesting little exercise.